supposedly in the future, and this we hope to do this in technology, the quiz on the lecture will be incorporated with the electronic presentation of lectures, so you don't have to take classes. And, you know, we're using the textbooks online only.
I think I still worry about having so many things online, where they can have someone else be doing the online homework for them. Like, how do you test that besides just you come in and you take the midterm?
Yeah, that's a good. I think that's a good point.
Because I have students that are struggling in my class, and yet they always get 100% on the homework.
Well, that's why you don't count the homework for more than enough to motivate them to do it.
But that's the if I may interject, that's just the online where you don't see their actual handwritten work, right? So,
Yeah, I don't know who is actually doing this.
so it's harder to actually cheat if there was a component where they have to write some stuff and scan it in, so that's their own handwriting.
Well, since they're here on campus, they're turning in handwritten homework free.
Oh, okay, there are.
When they complete their worksheets at home.
But they could still be working with someone and then just
But
copy the
Sure.
Yeah, that's all.
That's true. I mean,
We're never going to fight that.
But I actually, to be honest, in my experience at different universities with multimedia course presentation, it's actually a very good idea to have a concrete thing during class time that connects to what might otherwise be a very disconnected experience of watching a lecture. And so even though it does take a few minutes of class time, it's probably better to do quiz on the lecture during class than it is to do it online. I mean, it's more convenient for the instructor. But it gives a legitimacy to the lecture and the status of the lecture that it wouldn't otherwise have. So, yeah, and so there's less likelihood of person getting sick. As long as the quiz is like one or two questions that are more than surface. Once they figure out what kind of surface item is being asked, they should talk to each other, right? Yes. Yeah, I'm really fascinated by what y'all are doing here in combining the lecture and the section. Because San Diego, I mean, a lot of UCs do a similar thing with a live lecture and then these recitation sections.
well, that's what 50 years.
Yeah. But the difference is that the recitation sections are taking on more and more of the character of the things that you're doing rather than the TA solving problem on the board.
Yeah.
Which is what has happened. Right? Instead, it's the student solving problems.
Okay, it's also, I think, we wanted to reverse the ratio.
Thanks for letting us listen.
Times 10.
Also, I'm probably going to email you, so if you see an email from Shandy at UNCO or half at UNCO, that's me.
Sure. I hope I won't regret it again. I mean, it's not personal. I just got 150 emails last night.
Yeah, I know.
I'll remember.
Okay, thanks.
I wanted to reverse, and I'm recruiting Eric and Eric for the project, because I wanted to reverse the ratio of time spent watching lecture and time spent. So rather than having 1 hour out of 4 a week with a PA and then 3 hours watching the lecture, I thought I'd have about an hour lecture, you know, for calculus class, and 3 hours of active learning class, and that's what this has done. Now, I do know that some universities take up 1 hour recitation, 1 hour too. Yeah. And there are students who don't bother with live lectures, who go to the recitation.
Yeah. There are also students who don't bother to go to the recitation instead of the exam. Yeah. It's a trade-off.
I definitely had students that have said, I really prefer a lecture.
Well, I had a student in Eric's class today tell me how much he liked this thing.
Yeah, and I've had students telling me, now, are you teaching this for Cat 2?
Yeah, I've had a lot of students ask that. Sorry.
Yeah, how do you think they're going to fare?
maybe they won't be as fast at calculating stuff as their classmates, but they're definitely going to understand it a lot better. They're going to pick up stuff faster than the other students, but they're not going to be able to calculate stuff as quickly.
Maybe I was sitting down on prototype stuff, but working through stuff tomorrow.
I think they're going to form more study groups.
Yeah,
Yes, that's it.
I think they will be, attuned to the need.
Almost everyone that comes to my office hours, they come in pairs.
It's interesting.
protein story. You know,
Well, thank you for letting me
Yeah, thanks for
talk
coming.
with you. I'll see you at couple days after. So I have a for-profit thing.
Okay. Well, I'll see you in Andy's class.
Yes, sir, you will.
Email my office.
Yeah. Do you have a cell phone that takes text messages?
It's 916-806-803. And I've registered my phone at the house, so my ring is still on.
TEN, right?
Yes. Can you call me so that I can hear?
Yeah, yeah.
I do have a cell phone. Nobody has a phone.
Actually, don't get called that often.
Except for people who want to renew my car.
Fortunately, a few times I've...
notice for your car
Yeah.
warranty.
Yes.
There you go.
You guys have done that thing. Very good.
Yeah.
And that also takes text.
Anyway, I'll see you in class.
Danny, you're in science.
Yes. 264.
Can you try?
Actually, it's a really hard building to get around.
Okay.
So, what you want to do is go up to the second floor, look for the elevators, it's kind of in the middle, and then walk straight, and then it's right to your left.
Okay.
So,
And which building is the science? Is it the one?
The
that's-
yellow one.
Oh, it's the yellow
The
one.
cameras are this big. And you just put it in front. Cameras are very unobtrusive.
Yes.
I think the students completely forgot about them.
Yeah. I mean, I was walking around her room. In Eric's, we didn't get enough talent release for me to be able to move around the
Oh,
room.
I'm sure.
Nope. Just the way it goes. Sometimes it goes well, sometimes it doesn't go so well. Her class, pretty much universal talent. So I was walking around the room with my pole. Remember how sometimes in Eric's class I had the camera with a pole and I peered into groups, and I did that in her room. And I did it a couple times with the two groups I had camera with on in Eric's room. And they just totally are ignoring me. And I've only been there the one day.
It helps, I think, that David has become new classes, so they're used to
They're
other
used to
people
somebody else
being
being there,
around
yeah.
and walking.
That's good. All right.
Okay. You have a class in
Yeah.
Oh, do you? Okay.
Every other Wednesday I make it to class on Friday.
I was so happy to find my little camera bag. Hi, beautiful.
I like it.
David, Dr. Meredith?
That was very helpful for me to talk to you yesterday.
Oh, good.
Made me have some realizations.
Oh, that's a good thing, right?
Yeah.
Okay. So actually, your class is at 1 down the hall. This way. So I'm gonna ask. It turns out I may run out of those permission slips. I thought I made enough.
You want to go upstairs?
Yeah. Can I make? Okay, thanks.
You can take care of it.
Oh, I thought you left it.
He had, he left his hat on.
That's more important than my coffee.
3. ¿Paper esto o qué? Pues como a la 1 y... Ah, bueno. ¿Listo? A las 3. La vida de mucha gente va a cambiar hoy. I never realized that PhD decision day is the same as tax day. It's pretty appalling. Huh? The day that you're supposed to decide where you're going for your PhD. Today. Pretty much. I mean, everybody has this. It's kind of hard to tell what that means, but everybody has a deadline today. It's not clear to me what happens if you don't. Not clear to me what you're supposed to do. Huh? What kind of deposit? Really? I've never heard of that. Who's they? That's the thing, I mean.
I wrote, me and Ray are doing our project together now, and we wrote a proposal. But it's okay if I run it by Sercon and email it to you at 2:30?
Yeah, yeah.
Okay.
Yeah, I can take it by midnight, so take your time. He's there today. I mean, I just saw him. He's here.
Oh, yeah. Yeah, I have an appointment.
Ah, okay. Either way is fine. Did you guys start on that homework? Man, I was having so much fun. It's a good homework. I like it. Oh, that's what that stack of books was? You know, I was thinking, where are they teaching them that stuff? And then, of course, it's this class. Like, I need more sleep. It's a really good way to do it, actually. I was doing it by hand, and it's hard. You kind of know what you're supposed to do, but it's really hard to draw it. But I guess if you want to do the deformations, then you need, the books won't do. Because you need a different shape, I guess. You need tiny books.
I'm just showing him.
Yeah. What do you mean before? There were these two tunes just now, right?
Yeah, but before that?
No. I think that was it.
Okay, because it seems like...
That's how it looked last time, by the way. It was doing that. So. That's why I thought it might be recording.
Oh, look. You're okay. 95%.
Okay, we'll see. Do you have a way of seeing upstairs, Arik? Okay. So last time we talked about the case of monomial ideals in 3 variables, right? And maybe this is the main statement that I would like you to take from last time, that every single monomial ideal in 3 variables has a minimal Fourier solution by picture. And what I mean by picture is that there is some graph embedded in a two-dimensional surface, which tells you how to resolve the ideal. Okay? Just to remind you, what we said is that if the monomial ideal is strongly generic, then this is really easy if you're able to draw in these staircases, right? So maybe you're doing it in practice and finding that drawing these staircases is tricky, but in principle, if you manage to draw the staircase, then drawing the Buchberger graph is very easy, and the Buchberger graph is embedded in this staircase surface. That's in the strongly generic case. And if you're not strongly generic, if you're any monomial ideal, then what we said is that we can perturb the exponents a little bit, and when we perturb them, we make the ideal strongly monomial, strongly generic. Then we do what we do for strongly generic guys, and then we unperturb. This is what you will do in the homework to see in practice how that works. Okay? Now, this is all about 3 dimensions, but of course, when we have a statement like this so explicit, we would like to say, well, hopefully this works in higher dimensions, in more variables, right? But if you want more variables, then you're going to probably have more dimensions. So if we want a similar statement I don't want to make this very mysterious, because the fact is that this works in any dimension, and so there's a similar statement in n dimensions. Let's say, in n variables, but to do that, we need to live in higher dimensions, basically. We need to learn about how to draw pictures like this in higher dimensions. And so that means that all of a sudden we have to learn about polytopes. We need to learn about polytopes so that we can make sense of the story in more variables. That's a good question. So the question is whether this should be R2 or R3. And I do mean R2 because what I mean is the two-dimensional staircase. Yeah. So we kind of imagine it in 3 dimensions, but actually I drew it on the board, and the board is two-dimensional. Yeah. And that's what I mean here, really. Okay. And you can imagine that if I want n variables, then I'm going to need n minus 1 dimensions. And that means that maybe I can push this one more variable, and we can still draw pictures that we can make sense of. Okay. And that's the picture that I drew over here. So this is an example with 4 variables. It's a monomial ideal given by a lot of generators that instead of writing them here, I wrote them on the vertices of a polytope. Okay, this is a polytope, a 3-dimensional polytope. I hope you can see it, and I hope it looks 3-dimensional to you. It has 4 hexagons, 2 in the front, 2 in the back, and it has 4 triangles. Yeah? And so the kind of statement that I want to make is that if I want to resolve this ideal, I can also do it by picture, and this is the picture. Okay? So I'm always going to be able to draw some picture like this where the vertices correspond to the generators, okay, which is how it was last time. The vertices of the graph were the generators. And then the syzygies correspond to the edges. The second syzygies correspond to the faces. The third syzygies correspond to the 3-dimensional things. Okay? So I will be able to draw a picture like this and tell you that the minimal Fourier solution of this ideal has this form. Okay? So why does it have this form? Because what I'm doing here, hopefully I did it correctly, is, so first I need to say what the generators are, and there's 12 generators, right? 1 per vertex. Okay? 3, 6, 9. There's 4 triangles Each one has 3 vertices, and they're disjoint. So there's 12 vertices. Okay. Then the first syzygies are given by the edges of this polytope, and if you count this carefully, you're going to see that this polytope has 18 edges. Then the second syzygies are given by the 2-dimensional faces, and you can see that this guy has 8 faces, like we said, 4 hexagons and 4 triangles. And then now we're in one more dimension, which means that we need to go to the next step, and the third syzygies are going to be given by the 3-dimensional faces, which in this case there's only one, right? The whole polytope. So vertices, edges, faces, polytope. Okay. So this is the kind of thing we want to do next. So I want to start the class today by basically giving you a crash course on polytopes, which is what we're going to need. So what's a polytope? Well, in one dimension, a polytope is I don't know, what do you think it is? A polytope that's in one dimension. So if it's in one dimensional, it has to live in a line. And so the analogous thing of a polytope is just a line segment. That's the only one-dimensional polytope. The only thing that you can do is maybe move it around, make it longer or shorter, but that's it. In 2 dimensions, we can make triangles, we can make quadrilaterals, pentagons, etc. So basically we have one combinatorial family for each n, right? In 3 dimensions already, it gets complicated, right? Complicated or interesting according to your point of view. So for example, we have a tetrahedron, we have our cube, we have some favorite polytopes, like maybe, I don't know what your favorite polytopes are, but for example, we have the octahedron, the icosahedron, the dodecahedron. We like those because they are the 5 regular solids, right? So this is called the Platonic Solids because this has been thousands of years since people have been studying these things. They appear very naturally in nature. But I don't just care about regular polytopes. I care about any polytope. So that's an example of a polytope right there. And what I want to do is actually start to make sense of what these things mean in higher dimensions. Okay. So for example, one thing I want to say is that just as I have a kind of a smallest polytope in each dimension combinatorially, I also have one here which is called a simplex. Okay, and we saw them as simplicial complexes. A simplex is basically the next thing in the sequence. But by the way, I should have started in 0 dimensions. And in 0 dimensions, that's the only polytope. Question?
Do all polytopes by definition have to be convex?
So I haven't even told you what a polytope is, right? So for now, I'm just drawing some pictures, and but the short answer is that we will only care about convex polytopes in this class. It's almost true. So 4 dimensions, you have something called the simplex, which has 5 vertices. It looks like that. Okay. Can you see it? Well, no, I can't either. Okay, you're supposed to imagine that that's a 5-dimensional thing, but really the only thing that we're able to draw is what we call the skeleton, right? We can only draw the edges. And maybe if you have these 3-dimensional tools, you could draw maybe a 3-dimensional rendition of this 4-dimensional polytope, but this polytope lives in 4 dimensions. Okay? And we can try to see shadows of it, but we're not really going to see it. Maybe my favorite 4-dimensional polytope is the 4-dimensional cube. And the way you draw that thing is you take 2 cubes in 3 dimensions. I mean, yeah, you take two cubes in 3 dimensions, and then you kind of put them in, take the first one and then put the other one in the 4th dimension and then join them. Okay. So you just join all the corresponding vertices, and that's a 4-dimensional cube. Actually, sometimes people brag that they can see in 4 dimensions. Maybe you shouldn't be so impressed by that. You should really take the time to stare at this picture. Imagine what would happen is if you rotate it around. There are programs that you can look at this in, and you can make sense of why this guy is kind of made of 3-dimensional cubes. You can see a bunch of things that look like cubes, etc.
Yeah. Is this a good analogy to kind of think of it? You know, like when you're looking at 3D cube, you're really just like you're connecting two squares, just squares with like more squares. So it's like for the 4D cube, you're connecting two cubes with cubes.
Exactly. So the way that I build a 3-dimensional cube is that I take 2 squares, and then I join the corresponding edges. Okay. And so what I'm doing is now taking 2 cubes and joining the corresponding vertices. I'm sorry. Okay, so that, and there are other things, and there's no reason to stop there. There's a million questions you can ask. For example, what are the regular polytopes in all dimensions? This is a fascinating question. It turns out that in most dimensions there are only 3 regular polytopes, which are the n-dimensional version of the simplex, the n-dimensional version of the cube, the n-dimensional version of the octahedron. Those things exist in every dimension. And somehow these things are 3-dimensional accidents. The icosahedron and the dodecahedron only exist in 3 dimensions, and there are no analogous objects in bigger dimensions. And then there's 3 other weird polytopes that happen to be regular kind of accidentally. I think 2 are in 4 dimensions, 1 is in 5 dimensions, and then that's it. It's a beautiful, or 6 and 4.
Yeah.
The point is that basically there's these 3 infinite families, and then there's a few weird ones. Okay? It's a fascinating story, and you should have taken that class last year if you wanted to know about it. Well, it's still online, so anyway, so I proved this in class last year. So if you guys want to see it, there's videos on it. But again, our point is not to care about regular things. We care about any polytope. So what's a polytope? And like I said, we're gonna care about convex polytopes. So a convex polytope is something like this, which is the convex hull. So this stands for convex hull of some points, V1 up to Vn. So this polytope is going to live, let's say, in Rd, okay? And it's going to be the convex hull of endpoints that live in Rd. So what do I mean by convex hull? What I mean is that you're going to take, what you should think is this idea that, for example, a polygon is a convex hull of its vertices. Okay? So basically, it consists of the vertices and everything that you get kind of in between by connecting them. Maybe you've heard of the analogy of taking a big rubber band and then letting it snap onto those points. And what you get is the polygon here. The same analogy is true for, I guess, a rubber suit here. I don't know. And you do the same thing here. Well, the way that you say that mathematically is this. You consider linear combinations of your vertices such that the coefficients are non-negative and their sum is equal to 1. Okay. So, for example, what's the cube? The cube is the convex hull of its vertices. What are the vertices? Well, there's 8 vertices. And if this is the unit cube, let's say that it starts at the origin. So one of the vertices is, let me make these column vectors. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Those are the 8 vertices, and then the cube is everything inside it, basically. And this is basically where you can say, okay, now it makes sense for me to define what the n-dimensional cube is, because what are these 8 vectors? They are basically all the vectors of zeros and ones. Right? So there's 2 to the 3 of them. Well, if you want to define the n-dimensional cube, then by definition, this is going to be the convex hull of the points that look like this, epsilon 1 up to epsilon n, where each guy is 0 or 1. Okay? By definition, this is the n-dimensional cube. It's the analogous construction. And then you can start proving theorems about it. For example, it's clear already that the n-dimensional cube is going to have 2 to the n vertices, because I can make 2 to the n of these guys. Okay. Stop me at any point if you have questions, okay? This is all going to be very important from now on. So, okay. So the next thing that I want to do is be able to talk about phases. Okay? So for example, how is it that we can look at this picture and tell what the faces are? How is it that we can see that there's a hexagon here that's one of the faces? Or for example, in this cube. Let's actually talk about a real 3-dimensional example, which is this room that we're in. Okay? So imagine that this room is a cube. Kind of. It's a parallelepiped, I guess. And we want to know what the faces are. Okay? So what are the faces of this cube that we're in? Well, somehow we're used to kind of looking up and seeing the ceiling, looking down and seeing the floor. And that's basically what you do. Okay? And in the general polytope, you're going to do exactly the same thing. You kind of look in one direction and see what do you see. That's a face. How do I... Sounds easier said than done, but it's easier said than done. What's a face? Well, let me say that given so if W is a linear function, let's say from R to the D to R, then I'm going to define p sub W. So what's a linear function? Let's think concretely about our example here. We are in this room. Let's say that these are the x, y, and z coordinates. We're used to z being the vertical coordinate. Let's consider the linear function z. Okay, that's a linear function. And I'm going to define p sub W to be the set of points in my polytope such that the linear function is maximum at those points. So for example, what is it that I'm saying if my linear function is z? If my linear function is z, I'm saying out of all the points in this room, what are the ones for which the linear function z is maximal? Well, they're the ones that are the highest, and that's called the ceiling. Okay? So for example, if p is the cube and W is the function z, then P sub W is the ceiling. Okay. And that's how I'm going to define a face. A face is just going to be what I get when I look at a linear function. And you should think about this and realize that a linear function is nothing more than a direction. Okay? Any linear function is just taking dot product with some vector. And so what I do is basically, to specify my linear function, I just look in a certain direction and see what's the farthest points in that direction. Okay. So can you tell me, for example, how to define the edge between the ceiling and the back wall? You need to give me a linear function, right? And I mean, of course, I have to tell you what's x, what's y, what's z. Otherwise, so let's say z is in this direction, x is in this direction, and y is in that direction. So basically, you need to be as high as possible, so you put a z, and you need to be as far from this wall as possible, so you put a minus x. So the points that have maximum value of z minus x are exactly the ones defining that edge. So what I get is the back face. Okay. So this is called the W maximal face.